So today what we're going to do is 3.4, talking about horizontal asymptotes. And you'll see that we have a function here, and that function is composed of two parts, a numerator and a denominator. Numerator designated in blue, denominator designated in green. And we have two ways that we can write this. This is called factored format, and it's called factored format because it's factored into nice binomial chunks, x plus or minus something. And then the other format we have, this would be called standard format. And we like both formats. Both formats have pros and cons. And for many of the homework problems, if it's a difficult homework problem that asks you a lot of questions, you'll be given both formats. You'll be given the equation in factored format. You'll also be given it in standard format. And you have to know what information to extract from which format. So to go from a factored format to standard format, you would multiply, or in other words, you would FOIL all of this stuff together, and that would give you standard format. To go from standard format to factored format, you would factor. So that's how you go back and forth from one to the other. And again, we're not going to be asking you to go back and forth from one to the other, but it's just good to know how to do that. Once we have our function set up with the numerator, denominator, factored format, and standard format, we're going to ask a whole lot of questions. Where's the y-intercept? Where's the x-intercept? Where are the vertical asymptotes, and where are the horizontal asymptotes? So to find the y-intercept, you're going to set x equal to 0. And basically, you're going to find f of 0. When you do f of 0 in the factored format, that means that you're going to plug in a 0 for this x, and a 0 for this x, and a 0 for this x. The y-intercept is going to be negative f times negative g times negative h divided by negative r times negative s times negative t. Oh, and by the way, we've got an a and a b as multipliers out in front, so don't forget about those. That's what you would do if you were given something in factored format. If you were given something in standard format, then all you have to do is look at these last two terms. Because as you can see in standard format, when you plug a 0 into the top, this term's gone, this term's gone, this term's gone, and all you're going to be left with is a sub k, which is some constant number. It's not going to have an x term on it. So, and the same thing happens on the bottom. So when you do this in standard format, you're going to end up with a sub k divided by b sub k, which is a much simpler way to figure out the y-intercept. So when you're looking for the y-intercept, use standard format and just read it off, the numbers at the very end, the caboose, if you will, in this train of the polynomial. If you don't have standard format, then just plug a 0 in everywhere you see an x, and that will give you the y-intercept. That's the same technique that we used in Chapter 1 with lines. It's the same technique we used in Chapter 2 with parabolas. And it's the same technique we're going to use for rational function. Plug in 0, that will give you your y-intercept. When you look at the x-intercept, what you're going to do is you're going to ask yourself, where does n of x equal 0? When you're looking for x-intercepts, you just look at the numerator. So the answer to this is going to be f comma 0, g comma 0, and h comma 0. Those will be the locations of your x-intercept. If you then go to the vertical asymptotes, you look at the denominator. And those coordinates are going to be, and we're not going to write it as a coordinate, we'll say x equals r, x equals s, and x equals t. Those are the locations of your vertical asymptotes. So x-intercepts, you read them off your numerator. Vertical asymptotes, you read off the denominator. Now there's one more layer that we haven't talked about that applies to both of these, and that's multiplicity. There's multiplicity for x-intercepts, and there's multiplicity for vertical asymptotes. And I'll do the x-intercept stuff in blue, I'll do the vertical asymptote stuff in green. And so you can have an odd multiplicity, you can also have even multiplicity. So when you have odd multiplicity for intercepts, so here's my intercept, the graph is a pass-through. It looks something like this. And when you have even multiplicity with an x-intercept, the graph is a bounce back. It looks something like this. So odd multiplicity is a pass-through, even multiplicity is a bounce back. When you have vertical asymptotes, and we'll do these in green, odd multiplicity means that the function approaches positive infinity on one side and negative infinity on the other side. Even multiplicity, once again, we have a horizontal or a vertical asymptote. For even multiplicity, both graphs approach the same infinity. Either they both approach positive infinity or they both approach negative infinity. Now, there's another way that you can view this, rather than saying bounce back and pass through and stuff like that, is referencing the signs. When you have an odd multiplicity, the graph goes from positive to negative. The y values change their sign. And also, when you have odd asymptotes, one graph approaches positive infinity, the other one approaches negative infinity. So you could almost say that the graph changes signs relative to that vertical asymptote. However, when you have even multiplicity, the signs stay the same. This graph stays on the positive side. It never passes through to the negative side. Instead, it bounces back. It stays positive. And the same thing's true with your vertical asymptotes. They stay positive, either both positive or both negative. Okay, so odd multiplicity means you're going to have a sign change. Even multiplicity means that the signs stay the same. And that's sort of a mathy way of saying this. When you get into calc, you'll explore this mathiness. The characteristic of whether something changes signs or not is much more prevalent in calculus. So there are three types of horizontal asymptotes. And when we talk about a horizontal asymptote, we're actually referencing only this guy. So a horizontal asymptote only references ax to the n divided by bx to the d. This is all that horizontal asymptotes apply to. So the y-intercepts reference the caboose of the polynomial train. The horizontal asymptote references the engine. We put n and d up there to mean n is the power or the degree of the numerator n, and d is the power or the degree of the denominator. And these are important characteristics. So you can have three scenarios. You can have n greater than d, you can have n less than d, or you could have n equal to d. So these are the three scenarios you can have when it comes to the relationship between the degrees of the top and the degree of the bottom. So if n is greater than d, 3x to the fifth divided by 4x to the third. This is a scenario where your denominator is smaller, your numerator is bigger. So I call this one top heavy because the top grows faster than the bottom does because it's a higher power. So when you graph this, the graph is going to look something like this. Zip. It's going to go up to infinity. The top is going to grow faster than the bottom. This number is going to get bigger and bigger and bigger and bigger faster as you go out to infinity. And so this one, the asymptote, let me scroll down just a little bit. So for this, the asymptote does not exist. There is no asymptote on this one. There's no horizontal asymptote. This one just keeps growing and going to infinity. In the second scenario, you could have 4x to the third divided by 3x to the fifth. And this is one I call bottom heavy because the degree of the denominator is bigger than the degree of the top. So the bottom gets bigger faster than the top does. And when you have a denominator that gets bigger faster, that means you're dividing by a bigger and bigger number each time. And when you divide by a bigger and bigger number, the value overall approaches 0. It gets smaller and smaller. 1 divided by 10, 1 divided by 100, 1 divided by 1,000,000, 1 divided by 1,000,000,000. That number is getting smaller and smaller and smaller. And so this graph is going to look something like this. And there is a horizontal asymptote at y equals 0. When you have a bottom heavy function, the function itself approaches 0. The y coordinates get closer and closer to 0 as x goes out to infinity. Finally, you can have n and d equal to each other. 4x to the fifth divided by 3x to the fifth. Here what you have is the same power. This graph is actually going to have a horizontal asymptote, not at 0, but at y equals 4/3, which are the coefficients out in front. So in this case, your horizontal asymptote is at y equals a divided by b, which is the a and b right here at the very front of the train. So these are the three scenarios you're going to see. Top heavy, where it goes to infinity, no horizontal asymptote. Bottom heavy, where it collapses to 0, where the asymptote's y equals 0. And then if they're the same power, then it's the ratio of the coefficients in front. And we want to find the y-intercept. We want to find the x-intercepts. We would like to find the vertical asymptotes. So let's find these 4 things. And then we'll sketch a graph, of course. And you'll notice that we're given the function in standard format. So here's standard, and here is factored format. Y-intercept. And remember that the y-intercept is where x equals 0. So you could plug it in here into factored format, 0, 0, 0, 0, and then do a whole bunch of multiplication, and that's great. If you plugged it into standard format, this is gone, this is gone, this is gone. So there's your negative 8 over negative 9, which you then simplify to 8 over 9, right? But then you have to multiply by that negative 3 sitting out in front. And this is a negative 3 over 1, don't forget. So that's negative 3 times negative 8, which is positive 24. And then 1 times negative 9 is a negative 9. So it's negative 24/9. So that's the location of your y-intercept. What is negative 24/9 as a decimal, approximately? So we'll say this is about negative 2.6. Yeah, close enough. Just when we graph this, it'd be nice to say, oh, I'm thinking that's about 2.5. So, all right, x-intercepts. So for our x-intercepts, where do we want to focus our attention? Right up here. So let's see, I'll get you started on this. How about blank comma 0 and blank comma 0? So where are the x-intercepts? Yep. So negative 2, positive 4. Those are our 2 x-intercepts. And you just read that right off of the factored format. So for the vertical asymptotes, your focus is on the denominator. And these are going to be at x equals negative 3 and x equals positive 3. And then finally, for the horizontal asymptote information we're going to grab from this. And so we can see that these 2 functions have the same degree. One's an x squared and the other one's an x squared. So that means all we have to do is take a look at the coefficients. So what is the coefficient in this case? Or maybe I should say, where's the horizontal asymptote? Y equals, and we'll just say negative 3 over 1. Let's graph all this stuff. So I'm going to grab this, and I'll just slide it down here, like this. Okay, so there was a 3 there, and we said this was about negative 2.6-ish. Okay, so let's graph this. So we have a y-intercept about negative 2.6, right about there. We have x-intercepts at negative 2, bless you, and positive 4. We have vertical asymptotes at negative 3. So there's one here at negative 3. And there's another one here at positive 3. And we have a horizontal asymptote at negative 3 like this. Okay, let's sketch the graph. And we do have to preface, horizontal asymptotes are not like true asymptotes. You actually can cross over a horizontal asymptote, like in between the intercepts. The horizontal asymptote really describes the behavior as the function goes out to infinity on the left and to the right. Okay, so let's start and graph this. So here's our y-intercept. Moving to the right, which way does our line have to go? Up or down? It's actually got to go down because there's no x-intercept before that asymptote. And so the line actually goes like this. Zoop. Yes, it can go through the horizontal asymptote. And that's where horizontal asymptotes are not true asymptotes, in that locally you can actually cross them. There's no x-intercept up here before the asymptote, so it's got to go down. Now, knowing that all of our x-intercepts and all of our asymptotes are odd, okay, so there's all sign changes. If this graph approaches negative infinity from the left, what does it approach on the right? Positive infinity. So that means it's got to go up like this. And then it's got to come down and pass through the 4. So it's got to go through this x-intercept. And then how does it behave after this? It approaches that asymptote but never crosses it. So if we were to continue this line out, the graph would approach it but never cross it. So that's the graph moving to the right. Let's now graph it moving to the left. So again, starting at our y-intercept, we're going to move to the left. And which way do we go? Up or down? Up. Yep, got to go up through the x-intercept. So we're going to do this, zip, and approach that asymptote. And then because that asymptote is odd, if we approach positive infinity on one side, we got to approach negative infinity on the other side, like this. And we're bound by this asymptote right here. The horizontal asymptote deals with the values of the function as you approach infinities, whether positive infinity or negative infinity. We really don't care what happens locally, like on a small scale. It's more like zooming out and look at it in the infinities. How does the function behave? Let's see if we're even close. And what did we have for a function? There it is. And let's make this red. How's that? Oh, maybe we should put in some other stuff too. How's that? Look about the same? Yeah. So here's one where instead of giving you the equation and having you graph it and do all this stuff, we're giving you the stuff and asking you to come up with the equation. So you know that this is going to have the format f of x equals a over b, and then a bunch of x-intercept information on the top and a lot of vertical asymptote information on the bottom. Fantastic. So this is the structure. So let's say f of x equals, what does, and by the way, these are vertical asymptotes. So where does this information go? On the bottom. Vertical asymptote information goes on the bottom. So what do you want to write on the bottom? Yep. X plus 6 and x minus 2. And we're assuming these are all odd because they're not indicating that any of them are even, so we'll just leave them as ones. The next sentence, x-intercepts at -1 and -2. So where does that information go? On the top. And what do you want to write? X plus 1
and
x plus 2. Done. Third thing, horizontal asymptote at y equals 7. So that means that out front here, we have a 7 over 1. That's right. So if you were to write this entire function, I'd say f of x equals 7 times x plus 1, x plus 2, divided by x plus 6, x minus 2. And if we were to graph this, you would see that it would have vertical asymptotes at -6 and 2. It would have x-intercepts at -1 and -2. And it would have a horizontal asymptote at y equals 7. How could we make this more difficult? If we added more x-intercepts, if we added more junk to the top, would that make it more difficult?
Multiplicity.
Oh yeah, multiplicity. We could throw multiplicity in there. But even multiplicity, is that really going to make it more difficult? One way that we could make this more tedious, maybe not more difficult, but just more tedious, would be to add x-intercepts, right? Instead of 2 groups of parentheses on the top, let's put 15 of them up there, right? It's more tedious, but it's not really more difficult. You're just doing the same thing again and again. Same thing is true with the vertical asymptotes. We could just add more vertical asymptotes, right? But it just creates more work. It doesn't really make the problem more difficult. Multiplicity is kind of in that same boat where once you determine if it's even or odd, it doesn't matter if it's to the 2nd power or to the 102nd power. You still know that it's going to be a bounce back. So really, the suggestion of saying write your answer in standard format evokes a new thought process, right? It's not just tedious, but you've got to do something extra now at this point. So what we're going to do is we're going to FOIL this top part, and we'll get x squared plus 3x plus 2. And then we'll FOIL the bottom part, and we'll get x squared plus 4x minus 12. And then we'll have to multiply the top by the 7. So in standard format, f of x would be 7x squared plus 21x plus 14 divided by x squared plus 4x minus 12. And that's how you would write the equation in standard format.